Hello, welcome to this video about decoupling and bypassing circuits from EMI and EMC point of view. My name is Arturo Mediano. I am working at the University of Zaragoza, and I am a technical advisor of Y.I.C Technologies, and I am happy to show you how to understand this important problem using near-field scanners from this company, from Y.I.C Technologies. Let's start explaining the problem. So we have a circuit. Consider in my slide, this is a black integrated circuit. It could be a digital circuit, analog circuit, audio circuit, radio frequency circuit, power electronic driver, any kind of electronic circuit that is active. You can see that we need some kind of power supply. Typically, we can think about 3 volts, perhaps 5 volts, perhaps 12 volts, any kind of DC voltage. And we have an output. In my example, it's a clock signal. You can see a square wave signal with a rise time, a fall time, maximum amplitude, zeros and ones. And when I am interested in signal integrity, I am interested in this signal not being distorted in the path from the transmitter to the receiver. When I am interested in power integrity, the idea is that the voltage must be ideal, must be able to power the integrated circuit, to power your circuit, to be able to maintain this good waveform in the output. So in an ideal world, this is what happened. The problem doesn't exist. But let's think what happened in a real circuit. In a real circuit, the connection between the power supply system and the integrated circuit is made by, I don't know, traces, cables, wires, any kind of metallic connection. And in these wires, you have a current. It's the current that the integrated circuit needs to work. You have some kind of perhaps DC component, and you have some kind of AC component. AC means we have frequency. In the path from the power supply to the component, we have parasitic effects. Mainly, we have a resistive effect and we have an inductive effect. Usually, the most important effect in this connection is the inductive effect. Obviously, you have a capacitance from one wire to the other wire, but the most important effect is the inductance. Why? Because if you take the AC current and you consider that in this inductance we have a voltage drop, because anytime current is changing in an inductance, you have a voltage. Voltage is L didt. So if you have a voltage drop in this inductance, the problem is that from your ideal 3 volts, you don't have 3 volts in your device. You have 3 volts affected by the voltage drop. This is what you can see in the image below in the left column. The voltage is distorted, and as a consequence, the signal in the output, our square wave signal, is distorted. So how is the typical solution for this? This is not an easy problem, especially if you are in a very high speed electronics, but usually the important idea is to consider that using a capacitor in parallel with the power supply of your device, you have the opportunity to have the DC current coming from the power supply and the AC current coming from the capacitance. If you have these two components of the current going to the integrated circuit, the integrated circuit will be working perfectly because the AC current is not creating the voltage drop in the parasitic inductance. This is what you can see in the lower part of the image. You have a flat VCC, low ripple, and you have a good, in this case, a square wave signal. So this capacitor must be selected considering how much is the current you need to decouple. This is the big or a small size of the capacitor. You need to select the technology. You need to take care about the layout of the component, where you put the capacitor, and sometimes it's not only necessary one capacitor, you have to connect several capacitors in parallel to minimize the parasitic inductance of the decoupling network. This is the typical problem we find when analyzing signal and power integrity problems. Let's show you what happened in one example with the oscilloscope. In my example, I am using a digital circuit with a clock signal created by this component here. On the left, you have a power supply that is coming from the USB connector. And the 5 volts VCC line is the red color line that is in the top layer. What is the return path for the power supply? The return path for the power supply is going through these jumpers in a trace that is creating a big loop for my circuit. In this PC board, they have the opportunity to use a small loop working with a trace, a return trace that is exactly below the upper trace. But I will not be using this in my example. So remember, this is a 5 volts line powering my device, and return GND trace is in the lower part of the drawing. The output of the system is a clock signal that I am not interested in analyzing, but we will see what happened in this signal in the scope. So the first thing to do is to take the circuit, to power the circuit, and to see how is the clock signal and how is the VCC that is powering the device. Clock signal will go to channel number 1, VCC will go to channel number 2. And in the first experiment, we will not be using decoupling network. Okay, so now we have channel 1 measuring the clock signal and channel 2 measuring the VCC line in our clock. Let me deactivate the decoupling network. So now the integrated circuit will not be decoupled. There is no decoupling capacitor. So let's see how are the waveforms. We switch to the other screen, and you can see this clock signal that is clearly distorted, and we are going to activate channel number 2 in my Rod-and-Schwartz oscilloscope so we can see how is the voltage drop, the ripple in the power supply line. So let's go here, and you can see that the distortion in the output of the clock is following the distortion of the power supply line. Let me see what happens if we activate the decoupling capacitor. When we activate the decoupling capacitor, the ripple is reduced and the signal is recovered. So as I explained it before, this is a typical solution for the signal and power integrity words. Remember that I am using pigtails, so the signal is totally clear, and because I am using jumpers, the inductance of my decoupling network is not optimized. But how is the effect of this decoupling network in EMI? To do this, let me deactivate the decoupling capacitor again. Let me disconnect the voltage probes, and now let me see what happens if we scan the PC board using EMViewer. EMViewer is the software that in some kind well, so let's see how we can scan the PC board. To scan the PC board, we need the EMScanner. You can see that it is a flat surface, and we can find different cells. Below each cell, we have two small, very small near-field probes. So we have a high spatial resolution. In high resolution models of the scanner, we can go well below the millimeter if you are interested in the very small PCBs or integrated circuits. In our case, we have the PCB on top of the surface. We have the red color indicating that we are powering the device, and the decoupling network must be deactivated for our first experiment. We will be scanning not only the area of the PCB, we will be scanning the area around the USB cable that is powering the circuit. To be able to work with the scanner, we need to activate the EMViewer. EMViewer is the software, and you can see here that we can create different projects to make spectral scans, spatial scans, combined scans, different possibilities. You can see in the bottom right view of the camera, the top view of the device under test. And in yellow color now, what you see is the spectral scan in a previous exercise where my device was off. So this is nothing. It's a very small quantity, it's noise from the environment, so nothing special. To understand how the spectral scan is done, we open the node and you will see that we have the possibility to specify the frequency range of interest. We are going to scan from 10 megahertz to 300 megahertz and with a resolution bandwidth of 300 kilohertz. Our clock signal is 24 megahertz. That is because I am starting in 10. And in the probes menu, I have the possibility to introduce in the scan an overlay. An overlay is some kind of drawing or picture that will help the user to identify some specific activity related with some specific component or area that you are scanning. When you are doing a spectral scan, it's not necessary to activate all the cells. You can make clicks. Look at this. Anytime I do click, the cell is activated or deactivated. Okay, but it's not necessary to activate all the cells below the PCB because the activity is well around the circuit. So we make OK and we run the spectral analysis. You can see how the scanner is identifying the activity of my digital system. The first harmonic, 24 megahertz, the second harmonic, 48, and all other harmonics with different amplitudes. If you are interested in the spatial scan, I mean where some specific energy is in your PCB, for example, the second harmonic, we have the possibility to go to the peak and to go to the right click in the mouse, or we can open in the spectral node and a spatial node. In the spatial node, you will be able to establish what cells are of your interest, all the cells below the device under test, and all the cells below the cable. You will understand why this is very useful. And in the analyzer option, I will be selecting 48 megahertz for the frequency because I am interested only in the second harmonic. And then we start. When we start, let me deactivate the overlay. When we start, the scanner is scanning each cell, and remember in each cell we have two near-field probes for identifying different orientation of the magnetic field. We can start to identify how in my PCB I have a loop. This is the loop we were explaining at the beginning of the video. No? So the energy is taking basically the current, the high frequency current is taking the full area of the PCB. And that was the problem created in power integrity and that was solved by the decoupling capacitor. If we activate the overlay, we can see how this current path match with the position of the components. We can increase or decrease the opacity, and we can activate something that is very, very important, that is the 3D view. In the 3D view, we will be able to understand from the EMI point of view why decoupling is very important. The energy is not only in the loop of the PCB, the energy is able to go to the connector and additionally to go into the cable. Remember that only some tens of microhenries in your cable are able to make you fail at 3 meters in typical limits from international regulations. So let's see what happens if we repeat the test, but at this time with the decoupling network activated. Let me activate the decoupling network, and now we repeat the test, making run again. You can see that the scan is really fast. And now the idea is that deactivating the overlay, we will start to see that the red color is not around the full PCB. The red color now is located, concentrated on top or below, in this case, of the clock circuit and the decoupling network. Okay? Remember, my decoupling network is not perfect. We have some kind of inductive effects. But what is really clear is that in the area of the cable, the color is mainly blue, low amplitude. Okay? So if we compare without and with decoupling, this is without the decoupling network, this is with the decoupling network. This is the importance of the decoupling network, is the capability to contain electromagnetic energy in the area that is not dangerous for other systems. If we see in 3D view, we can see something similar to my previous experiment. You can see how the energy is basically in the area of the component and the decoupling network, but when we were testing without the decoupling network, the energy was basically distributed around, really around the full PCB and going into the cable. So I hope you enjoyed the video. Remember that you need to take care about the decoupling of your circuits, analog, digital, power, radio frequency, or any kind of active circuit. And if you are interested in more interesting information, you can go to the Y.I.C Technology website and you will find technical notes, application notes, and more videos. So I hope to see you in the next video. Bye bye.